topic of this lecture is classification of second order PDE and canonical forms. We'll cover these 2 points in this lecture: classification of second order ODE and canonical forms. So let us start. Consider the following second order semi-linear PDE, which is given by this, where f, x, y, z, p, q need not be linear and is a Cauchy-linear partial differential equation, where the R, S, T, all this have a usual meaning, which is given by this. And the coefficient, this capital S, capital R, capital T, may be function of x and y with condition r square plus s square plus t square is not equal to 0. This is our assumption. And R, S, T are continuous functions of x and y. We further assume that these functions possesses continuous partial derivative with respect to x and y. That all are assumption. Now the given PDE, which PDE? This PDE, it is said to be elliptic. When it is called, if s square minus 4 rt is less than 0. If this is less than 0, it is called elliptic. If it is called parabolic if s square minus 4 rt is equal to 0, and if it is hyperbolic if s square minus 4 rt is greater than 0 at some point x naught y naught. So whenever you are having these types of equation, and if you are told to classify into elliptic, parabolic and hyperbolic form, you compare and you find the value of RST, which will be the coefficient of r, small s and small t, and find these values. And accordingly, you decide is it elliptic, parabolic or hyperbolic. Now let us see this problem. Reduce the partial differential equation this into canonical form. So let us see the solution. To reduce the above equation in canonical form, we apply some transformation by changing the independent variable xy to xi eta by this relation. That is, xi is a function of xy and eta is a function of xy. Where what are xi and eta? Xi and eta are continuously differentiable functions that we'll suppose, and we assume that Jacobian, that is evaluated like this, that is xi x eta y minus xi y eta x is not equal to 0. That will suppose. So that what will be the benefit of this? The transformation is invertible, at least at locally. Now, as we have seen in the previous lecture also, this we can calculate it and have usual meaning. So this you can find very easily, and you can write whenever this problem comes. You can write these values as it is, and you can go move ahead. Now substituting the values of this P, Q, R, S and T as we have found in equation number 1, we get, what is equation number 1? That is the main, this is our equation number 1. Here we'll put these values, which we are finding over here. P, Q, R, S, T, all these values we'll put. So that this equation will become, this will come in this form. This will become in this form, where what is AUV? AUV is RU square plus SUV plus TV square. So if we put in place of u xi x xi y, so it will become xi x square. It will become xi x square plus r into xi x square plus s into xi x xi y plus t times v square. So it will be xi y square. Like this way it is defined. And the 2 times b u1 v1 u2 v2 is this expression, where this is written over here. So in place of u1 v1 u2 v2, you can place this value. So we'll get the expression in this form. Now we can show that also you will have to write as it is, because it is verified that this expression is equal to this expression, where j is given by this Jacobian. Now keep in the mind that this expression is important. According to this value, we'll decide if it is parabolic, hyperbolic, or elliptic. So let us move ahead. First case, if s square minus 4rt is greater than 0. So under this assumption, s square minus 4rt is greater than 0, this equation, because it is a quadratic equation, we know if this happens, this is simply the discrimination. In this case, it will have a real and distinct root. So two roots will be there and they are real. So let these roots be. What will be the root? We don't know. So we are going to assume that these roots are lambda 1 and lambda 2. And we select xi and eta because we have to transform the x and y with xi and eta. So we are selecting xi and eta such a way that xi x, that is partial derivative of xi with respect to x, is equal to lambda 1 partial derivative of xi with respect to y. And similarly, eta x is equal to lambda 2 eta y. But this gives xi x is equal to lambda 1 xi y, and this implies xi x minus lambda 1 xi y, it is equal to 0. Now what is this? This is a first order linear partial differential equation, and we know how to solve this. We know this is solved in this way, that is del x by, because this is nothing but del xi by del x minus lambda 1 del xi by del y is equal to 0. And we know how to solve this. This is solved by taking these types of equations. So this is del x dx by 1 because the coefficient is 1. Here the coefficient is minus lambda 1. So this is coming over here and it is 0. So it is coming 0 over here. This implies therefore d xi is equal to 0 from this expression, that is xi is equal to constant. And using this 2 now, when we solve this, we get this differential equation. Similarly, if we take this second set, using this, we get the second equation, and we get similarly as xi is equal to constant, we can find that eta is equal to also a constant. So, and we don't know the solution of these two at present, so we can have a supposition. So let us suppose that the solution of this equation may be f1xy, which is equal to constant, and f2xy, which is equal to constant. So from this two, that is xi is equal to constant and f1x is equal to constant, we get the first value is xi is equal to f1x, and similarly we get eta is equal to f2x by taking eta is equal to constant and the second value f2x, so we get the second value. So by this way xi and eta we have obtained. Now as we assume that xi x is equal to lambda 1 xi y, we have, when we calculate this value that is given by this expression, we know, and by putting xi x is equal to lambda 1 xi y, we can find this out, and this is become this expression. But lambda 1 is the root of this equation. As lambda 1 is the root of this equation, so this simply becomes 0, and we get xi y square into 0, which is equal to 0. So similarly, as we assume that eta x is equal to lambda 2 eta y, and lambda 2 is root of this, we have this a into eta x into comma eta y is equal to 0. So these two things we have obtained, that you have keep in the mind that this is equal to 0 and this is also equal to 0. But because of this, from this equation, as we have seen this equation here, these two values, these have become 0, and because this is not equal to 0, this Jacobian is not equal to 0, and this is also greater than 0. So we get that b square is not equal to 0. So that b is also not equal to 0. And from this equation that we have seen previously, this is 0, this is 0, and this is not equal to 0. So by taking this 2 times b, this side means dividing b with this, we get finally an expression xi z eta z xi eta is equal to, say, g, a function of xi eta z z xi z eta. So simply dividing this by b, to b, we are getting this. So which is required canonical form for the hyperbolic PDE. So in this case, we have easily found this. So let us just recall what we have done. This was the case, and we have assumed this. From this, we have found two values. We have solved this and this equation we have obtained. And from this, we have supposed that these are the solution. Then we have found these two values. And using these two values, we have shown that this is equal to 0 and this is also equal to 0. Because of this, we have found that b square is not equal to 0, so b is also not equal to 0. And then using this equation, because this is 0, this is 0, and this is 2 times this, so taking this only this side and using this one and this one, we have found this. So which is required canonical form for the hyperbolic PDE. Now let us see the remaining two that are very easy and same to this. So let us take case number second, when s square minus 4 rt is equal to 0. Then the equation, as we have seen in the previous case, has a equal roots. Why it is equal root? Because this discrimination is equal to 0. So it will have an equal root. Let us suppose these roots are lambda 1 is equal to lambda 2 is equal to lambda, say. And we select xi is equal to f1 xy, as we have seen in the previous case, where f1 xy is a constant, is a solution of this differential equation, as we have seen in the last slide. Now in this case, we take eta, any arbitrary function of xy which is independent of xi, that is, it should not be multiple of xi. So you can take any eta in this case. Also, since a xi x xi y is equal to 0, so s square minus 4t is equal to 0, because this is 0 and this 2 is 0. So from the equation 3, which is equation 3, this is our equation number 3, this is 0 and this also is 0. So we get ultimately the beta is equal to 0, because this side is 0, this is 0, and this is also 0, that we can show very easily. So that this is 0 and this is 0. So from equation 3, we have b is equal to 0. However, this is not equal to 0. Why it is not equal to 0? Otherwise, the xi will be depending on, eta will be dependent on xi. And we are taking the eta such a way that it is independent of xi. So using a is equal to 0, b is equal to 0 in equation number 2, we get this expression. Which is equation number 2? Let us just see. This was our equation number 2. So here we have found this is equal to 0. This is also equal to 0, as we have seen in the case number 1. This also in case number 2, we can prove it is 0. And this is not equal to 0, because otherwise eta and xi will be dependent. So from this, we take this, and taking this side, we get ultimately the result as that z eta eta is equal to this, which is required canonical form for the parabolic partial differential equation. Now the case number 3, it is very similar to case number 1. Here s square minus 4rt is less than 0. In this case, the roots of this are, in this case it will be imaginary root, and therefore xi and eta will take as a complex values. So alpha plus I beta and eta is equal to alpha minus I beta, where alpha beta, so that in this case alpha will be this and beta will be this with the transformation. And using this transformation, as we have seen in the case number 1, we will have this, which we can verify it very easily, and you can directly write, using this you can directly write wherever it is required to solve. And proceeding in this case, we have z alpha alpha plus z beta beta is equal to 5 times alpha comma beta comma z alpha comma z beta, which is required canonical form for the elliptical partial differential equation. So in all these 3 cases, you can prove that what are the final result. In case of 3, the result is this is the canonical form. In case of 2, this is the final canonical form, and in case of 1, this is the final canonical form. So by this way, this question can be solved. So thank you very much. You can find the link of this PPT in the description box. Thank you.